Hey guys, it's Andre from the High Performance Academy, and I'd like to welcome you to our very first episode of HPA Live. So this is going to be a regular weekly show that we're going to be broadcasting live on our Facebook page. So the idea behind HPA Live is that we're going to be presenting a whole lot of information that's perfect for anyone out there in the professional tuning market. Or if you're just a car nerd and you want to learn more about EFI tuning technology and what is going on in the market. Hopefully these shows will allow you to learn a little bit, and we're also going to be keeping you up to date with the latest technologies, the latest products out there in the tuning market. We're also going to be keeping you up to date with the latest goings on around HPA Labs. You'll get a little bit of insight into what exactly Ben and I are doing at High Performance Academy. Now, we're calling this HPA Live right now. We're not 100% sold on that, so if you've got any better ideas or suggestions for a great catchy name for this show, we'd love to hear from you. Please post that in the comments and we'll take all suggestions on board. We're not aiming for Bodie McBoatface or Tuna McTunaface or anything like that, so let's come up with something relevant and catchy, please. So again, this is our first show. Bear with us. Hopefully we're not going to have any technical issues. Please be a little bit patient while we find our feet with this show and figure out exactly how it's going to go. In this particular episode, our very first one, we're going to be covering the Plex Tuning Micro SDM dash display module. We're also going to be looking at a pedal shift video that we've just recently launched on our Facebook page. We'll talk a little bit about that. We're also going to cover a couple of questions from some of our social media channels. So we'll answer those questions in this show. Hopefully it's going to help out a few of you out there with similar questions. We're also going to go over a short lesson on electronic closed loop boost control. We'll see exactly how that works. We'll cover a couple of the latest videos that we've recently launched on our High Performance Academy's YouTube channel. And finally, at the end of this show, we will be having a section for questions and answers. So if you do have anything that you want to know about the topics that we're talking about or anything tuning related, at the end of the show, that's the perfect time to ask those, and I will be answering as many as I can get through. So let's start by talking about the Plex Tuning Micro SDM module. So I've got one sitting right here, and this is a very recent product that Plex Tuning from Greece have launched. And basically what this product is, we'll have a quick tour of it in a second, but I'll just tell you exactly what it is. This is a micro driver display module. It's really nice and easy to mount because it's so small, and in its simplest form there are two products that they offer. The Micro SDM 100, which has just 4 wires, power and earth, and then it communicates via CAN, so it's got CAN high and low. So there's only 4 wires, which makes it perfect if you're going to be mounting it on a steering wheel. You don't have so many cords or wires to try and run back across the steering wheel back to the car itself. The 102 module, which is the one I've got here in front of us, is slightly more advanced. This allows you to actually run some switches or potentiometers back into the Micro SDM module, and then you can configure those switches or inputs to do whatever functions you want inside the software and send the state of those switches back out again via CAN, where it can be received by your ECU. So again, this is a great way of mounting some driver switches on your steering wheel, perhaps traction control, boost control, or even something simple like a pit lane limiter. Rather than having to run all of those wires back across the steering column, you can just simply connect them all into the Plex Micro SDM and then run the cabling through with just CAN high and low, power and earth, and send those signals via CAN back to your ECU. So let's have a closer look at the product anyway. So as you can see, it is really small. It's all housed in a really high quality CNC machined aluminium enclosure, and it has a single color OLED display. On the right hand side we have a couple of buttons, so again it's not particularly difficult to control at a touch. We've got the bottom button here will change the page that's being displayed. The top button also is used as a peak hold function. We've got a little LED indicator to show exactly what's going on. We'll see all of that in action in a second in a quick video we put together. Now, as I've said, this is the slightly more advanced 102 module, and you can see it's got a wiring harness attached to it. In this case, it's actually got two thermocouple amplifiers built in as well, so you can run thermocouple straight into the unit. You can wire up your switches, and then, as I've mentioned, it's really simple just to connect the 4 wires back across your steering column. We've also got a port for a USB connector where you can actually program the module. So it's a really neat and tidy little product, and at the moment I believe their base unit is priced at 390 euros, I think. Don't quite quote me on that, and I think on the current exchange rate that works out to be about 450 US dollars. So it's a fairly well priced product if you want a simple and really configurable display. Talking about configuring it, let's just have a quick look at my laptop, and first of all I'll go through the software that you can use to configure it, and we'll have a quick look at the video I put together. So this is the Plex Manager software, and you can see in this particular section here we can set up a number of displays to essentially show whatever you want to see on the screen. So this one will show you a preview here on the right hand side of what this particular display will show us. You can see at the moment it's just showing a single parameter of wheel speed. If we go through, we've also got some functions that you can set up. It really is quite powerful for the size of it. You can see that we can set up a shift light, so you can actually use it as a shift light module if you want. You can also set up some alarms as well, so if anything goes outside of bounds, you can use it to bring that to your attention. You can use it as an odometer, and you can also use it for lap timing. Move through and we'll have a look at the device configuration. So this makes it pretty easy to install it on just about any aftermarket ECU. As I've mentioned, it does get all of the data from the ECU via CAN or controller area network, pretty common on most late model factory vehicles as well as the current crop of standalone aftermarket ECUs. If we click on the CAN template, you can see a drop-down box open. So for most of the popular ECUs, it's as simple as selecting whatever ECU you have it connected to, and then the data will be available straight onto the micro SDM. If we click on the CAN bus receive, this shows all of the data that's coming through, all of the different parameters or channels that are coming through. We can also, if you're feeling adventurous, you can write your own CAN template to receive any data you're sending out, or you could reverse engineer the factory CAN bus and get all of the data that's on the factory CAN bus for a factory ECU and display the parameters you want on the micro SDM. Let's have a quick look at the video that I've just shot of it installed in our Toyota 86. This just gives a better idea of how the system functions. So on this particular screen you can see I've got lambda and the short-term fuel trim shown. Now if I just click the top button there, that's the peak hold function that I mentioned. So you can see there on the left hand side the two parameters are shown solid, and this will show the current highest value since the unit's been running. We'll go back to real time, and if we click the next button, this currently shows our current boost pressure as well as our current aim boost. The next screen is one that I've configured for our Toyota 86 with a flex fuel system. You can see it's showing us the current ethanol content as well as any of the trims being applied to boost, fuel and ignition as a result of that ethanol content. Next we've got a screen that's just showing some of the temperatures in the engine. So we've got engine temperature, air temperature, oil temp and fuel temp. On the next page I've just displayed fuel pressure and oil pressure, and again if I click that peak hold you can see it shows the peak oil pressure in this case from that little blip that I gave it on the throttle. On the next screen, if we go across, I've also got individual cylinder lambda sensors on this particular engine. So that's just a quick tour of the Plex Micro SDM module. It's not often I sort of see a new product in the market that really is quite innovative and actually excites me, I guess, and this is definitely one that I've found really interesting. And I think for the price as well, like it's a struggle for a lot of people to justify spending perhaps $1,000 or more on a full function dash display unit, and this really bridges that gap and gives you just that little bit more functionality than your factory gauge cluster without going to the expense of a fully fledged dash logger unit. So if you're interested in finding out more about the Plex Micro SDM, I'd suggest that you head to Plex Tuning's website and you'll be able to find out more there. Now, moving on, the next aspect we're going to talk about is our paddle shift video that we've just released. So again, on my laptop I've got this video here now. We were at the racetrack just a couple of days ago and did some testing on a Hollinger 6-speed sequential gearbox fitted with paddle shift and controlled by a Motec M150 ECU, and that was quite an interesting exercise. So we decided to take the opportunity while we're at the track to make a short video of what we were doing and explain exactly how the paddle shifted system works. So if you're interested in watching the full video, that is currently on our Facebook page, and actually after this is aired live, you can scroll down about 2 or 3 posts and you'll be able to see that video. So it goes over in a little bit more detail than what I can do right now, how the paddle shift system works and how you can change gear with a modern ECU without using the clutch, and how the ECU can match revs on the downshift. So check that out, it's on our Facebook page, as I've said, probably about 3 posts down from where you are right now. Okay, we're going to have a look at a couple of questions that we've had on our social media channels. And if you want your questions answered on our live show, please make sure that you do ask questions on our social media channels so we can get those questions and pass them on. What we're looking for here is common questions that people have, so we can answer these questions live and answer some of the most common questions people really want to know about. So on this particular post, we had a shot of a 2JZ engine fitted into a Subaru WRX, and this particular engine is designed to make upwards of 1,000 wheel horsepower on E85 fuel. And those of you who are aware of the requirements of ethanol fuel E85 will know that you do need a lot of fuel flow to support that sort of power. So we had the post itself was about staged injection, and you can see here we have 2 fuel rails and there are 2 separate sets of injectors fitted to the engine, 2 injectors per cylinder. So we can see here on cylinder 2 we've got a primary and a secondary injector, and this is quite a common technology, particularly on engines that are making really high specific power levels, and again on ethanol or methanol fuel in particular, where we need to supply a really large volume of fuel to the engine in order to support the power the engine's going to make. So the first point is, why do we need staged injection? We could, of course, fit one single large injector that can simply flow enough to support the engine. But the problem with this is really large injectors tend to offer really poor control or poor linearity down at very short pulse widths, the sort of pulse widths that we're going to need to get really good control of the air-fuel ratio at idle. So if we fitted a single large injector, sure, it might work great at high RPM, high boost, and it will supply the fuel we need, but we're going to end up with an engine where we can't control the idle mixtures, and generally fuel economy, idle quality, and cruise is just going to suck. So the idea here is we fit 2 injectors instead, and at low loads where there's not a huge requirement for fuel flow, such as idle and cruise, we're primarily using a single injector. as the RPM, the boost increase and we need more and more fuel, we can stage in the secondary injector. So the first question we have here is from Nico333, who asks, twin injector per cylinder, that must be a ball lake to map. Now, personally, I've never had a ball lake while I've been on the dyno, but I do get the question there. And the reality is with modern ECUs, when you've got stage injection like this is a pretty common technology these days. And when we've got the stage injection set up properly, it's actually pretty seamless. We're really just focusing on setting up the staged injection, telling the ECU how many injectors are fitted and what size they are. Then we can tune our main fuel table, and we'll have a table where we can tell the ECU what percentage of fuel is to be delivered by the primary or the secondary injectors. And really the ECU takes over the hard work, and everything just happens in the background nice and seamlessly. So when it's set up properly with a modern ECU, no, it's honestly no harder than tuning an engine with a single set of injectors. The other question on the same post that we had is from Tankosaurus Rex, who asks, what's your thoughts on twin feed rails? So just to clarify, and in this particular picture, you can see, or you can almost see, we've got feeds from the fuel pump on both ends of the rail. So we've got one at the front of the rail, and obviously it's hidden behind the scuttle panel. We've got a feed into the other end of the rail as well. And what you can see is that the returns come out the center of the rail. Now, this isn't particularly uncommon, particularly on really high horsepower cars. And what you can find is that if you use a more conventional approach where you feed the fuel in one end of the rail and you return out the other end, particularly on an inline 6-cylinder where that rail by necessity ends up quite long, what you can find is that at very high injector duty cycles where we're flowing a lot of fuel through the injectors, we can actually find that we get a pressure drop off through the rail, or that the flow of fuel decreases as it moves through the rail. So what can happen essentially is the injectors at the feed end of the rail can end up receiving more fuel relatively speaking than the ones at the far end of the rail. So the dual feed idea gets around that by feeding fuel in both ends of the rail, and then the excess fuel returns out the center. I've used it myself in a number of drag cars, and I've found really good results from it. So that's generally why we would use a dual feed system. Let's move on, and we've got another question here on our Facebook page. And this is a post we did a little while ago on electronic boost control, and we've got a question here from Corey Engel, who asks, what's the reason for tuning open loop boost control? Unless you have a faulty sensor, of course. I don't understand why closed loop boost control wouldn't always be the ideal option. And that's a really good question, Corey. However, when we're talking about closed loop boost control, the ECU still needs to start from somewhere. And generally, my own guide for tuning electronic boost control systems, what we want to do is make sure that before we engage closed loop boost control, or try and get the ECU to correct any errors between our current boost pressure and our target boost pressure, we want to make sure that the boost pressure is as close to our target as possible in open loop. So that's where there's no feedback. And what we need to do in order to achieve this is tune, depending on the ECU you're actually tuning, it'll be called a variety of things. It might be called the base wastegate duty cycle table, it might be called the feed forward table, or it might be called the normal position table. Essentially what it is a table that defines the wastegate duty cycle solenoid position for a certain RPM before the ECU tries to correct. So what we're trying to do is tune that particular table in open loop to get our boost as close to our target as we can. Now the key here is if we've got our open loop boost control tuned really well, in that case the ECU is going to have very little work to do in closed loop, and we're going to get much better control over our boost pressure. So even when we're relying on closed loop boost control, we still need to start with a stable and accurately tuned open loop boost control system in order to get the best possible results. So that particular post there actually leads nicely into the next section, where we're going to have a quick look at closed loop electronic boost control in a little bit more detail. But remember, if you do have any questions on any of our social media posts that you'd like answered, please comment on them, and we'll be picking some of the most common ones or most popular questions we see to cover in our upcoming episodes. So let's move on to our little lesson on electronic boost control. And what I'm going to do is I'll present some information here that I've got from our turbocharged Toyota 86. And this is running on a Motec M150 ECU. So some of the aspects we're going to be looking at here will obviously be specific to the Motec M1 ECU. However, it's the fundamental principles that are really important here. So first of all, what is closed loop boost control? We've just kind of talked about that, but with closed loop, regardless of what we're talking about, it might be closed loop boost control, it might be closed loop lambda control. What we're looking at is using the ECU to measure the parameter we're trying to control, in this case boost pressure, comparing it to our target or desired boost pressure, and if there's any error, then the ECU can adjust the wastegate duty cycle in order to try and drive the boost pressure towards the target. So in this case, we're doing exactly that. We're looking at our boost pressure, we've got a target boost pressure table, and we're allowing the ECU to adjust the wastegate duty cycle if there's any error. Now, why is this better? The alternative, of course, is we have an open loop system where we just apply a fixed duty cycle to the wastegate. And that's a pretty simple way of tuning boost control, and it can also be incredibly effective. The problem with this is it's a passive system. There's no feedback. So if our boost pressure ends up higher or lower than our target, the ECU is not going to do anything in order to try and correct this. Typically what it's going to mean is we're going to see our boost pressure lower in the lower gears where there's not as much load applied to the engine, and we're also going to perhaps see more boost in the higher gears and maybe more boost on colder days where our air temperature is lower, we've got higher air density. And this really comes back to another aspect with boost control, and really boost control is one of the hardest aspects in EFI tuning to really get right. And one of the reasons for this is when we're tuning boost control, we're talking about a system that's constantly moving. We're talking about a system where the parameters we're trying to control are always changing. For example, our exhaust gas temperature, which has quite a dramatic effect on our boost control, that's always changing depending on how hard the engine's being driven. Our ambient temperature and our ambient or barometric air pressure are always changing. So it does make it really hard to get really good, accurate control, and that's where closed loop control comes in. So let's have a quick look at the laptop now. We'll go over the parameters that we've got for our Toyota 86. So we start off in the M150 software, and the first place we're going to look is our boost aim main parameter. And you can see there's a lot of parameters here. Don't worry, I'm not going to get too in depth. We're just looking at the basic ones that matter here. And if we full screen this, we can see we have a simple two-dimensional table which is targeting, in this case, 60 kPa gauge of boost pressure, regardless what our engine RPM is. So that's what we're asking for from the ECU, 60 kPa of boost pressure. Now remember, I mentioned that we really want to start by tuning the open loop control system first so that we're as close to that target as possible. In Motec lingo, that's known as the boost control feed forward table. And if we click on that, we can see that we've got, in this case, a three-dimensional table of wastegate duty cycle versus engine RPM. So we've got engine RPM on the horizontal axis. In this case, we've also got our boost aim on the vertical axis. So we can essentially drive the wastegate solenoid at different frequencies based on our current boost target and our engine RPM. So this table is designed to get us really close to our target first. Let's have a look at the time graph here, and I'll just full screen this so we can see exactly what's going on. So this was from a dyno run that I performed a little while ago, just before we came on live. And first of all, we've got, I'll just go over the parameters that are being logged. At the top, we've got our engine RPM, so we can see what the engine speed was doing during the run. Below this, we've got our turbocharger speed, which I'm going to talk a little bit more about later. Next, we've got our inlet manifold pressure, throttle position, and exhaust manifold back pressure. We've got our exhaust lambda versus our target air fuel ratio, or lambda. The parameter that we're really interested in, or the group that we're really interested in, first of all, is this one here, where we've got our boost aim and our boost pressure. So let's just see if we can make this a little bit bigger so we can see exactly what's going on. So we have a blue line here, which is our boost aim. And remember, from that 2D table, our boost target, it was constant at 60 kPa. So you can see that blue line just sits there at 60 kPa the whole way through. Our green line, however, this is our actual measured boost pressure. So this is what the engine's doing. And we can see at the start of the run, 2000 RPM, just at the beginning of the dyno run, we've got 19.8 or just about 20 kPa of positive boost. So the turbo doesn't have enough exhaust gas energy to produce our target boost pressure. As we come up, you can see that the boost pressure rises quite quickly, and we actually get a small spike, a small overboost. We've gone to 63 kPa, so just 3 kPa over our target. As we move through, though, you can see that our boost pressure and our target are always very, very close. So this is a pretty good starting point for our boost control. So let's talk about how the ECU can make adjustments to this. How does the ECU actually control our boost pressure? And that's done via what's known as a PID control algorithm. It's a really common way of controlling any closed loop system where we're looking at a measured value and a target. And the PID aspects refer to proportional, integral, and derivative gain. Now, I don't want to get too involved with exactly what those mean. I don't want everyone dropping off to sleep while they're watching this. But what we can see in this particular group that I've just made available here, we can see that the parameters, our proportional, derivative, and integral gains are being logged. And the important point to see here is this shows what the ECU is currently doing in order to correct any errors in our boost control. So we can see particularly as we came up on boost initially and we saw that slight overboost, if we look at our proportional gain here, the blue line, we can see that that drops down quite rapidly, and we actually see that it goes negative. So it's removing, in this case, 5.2% from our wastegate duty cycle in order to help bring the boost back under control. And what the ECU is doing the whole time is it's looking at the boost control error, which is the next group down here. And this is showing what the current error is between our target and our measured boost pressure. So when we get this right, what we end up with is rock solid boost control, where the ECU can first of all get a really good starting point using that open loop feed forward table. So it's already going to be really close to our boost target before it gets started. And then it's going to be able to apply the closed loop control in order to correct any remaining error. Now, one thing that's not quite related to this, but seeing as I've got it here on the screen, I'll just show you. Remember I mentioned that we were logging our turbocharger speed, and you can see down the bottom we're also logging our inlet mass flow. Now, these two parameters are quite useful, particularly when we're doing development work around turbocharger selection on an engine. If we swap through to this particular graph here, this is a compressor flow map or compressor map for the Borg-Warner EFR 6758 turbo that we've got fitted to our Toyota 86. So you can see in this case we've got what's known as pressure ratio on the vertical axis. So essentially this is the inlet pressure, the outlet pressure that the turbocharger is producing divided by the inlet pressure. So this lets us know the pressure ratio. And then we have on the bottom axis we have corrected mass flow. So this is mass airflow. In this case it's being presented in metric units of kilograms per second. And the other aspect, you can see that we have some lines on our compressor efficiency map which show the turbocharger speed. So using this particular compressor map, using our turbocharger speed, our pressure ratio and also our mass flow, we can see exactly whereabouts we were operating at any particular point in our data log on this compressor map. We can see exactly how well suited this current turbocharger is to the way we're using it on our engine. So that's a really quick look at closed loop boost control, how it works and why you should be using it if you've got an ECU that's capable of doing it, as most modern standalone ECUs are. If you want to learn more about tuning closed loop boost control, you want to learn more about those proportional, integral and derivative gains, we do have a really in-depth boost control course that covers all of those aspects and goes through a worked example of exactly how to configure and tune closed loop boost control on the dyno. If you're interested in looking at that, check it out on our website. You can find it at www.hpaacademy.com/courses, and that course is valued currently at $79 US. All right, let's move on. And the next aspect we were going to look at is a couple of the recent videos that we've just released on our YouTube channel. So the first one we've got is we shot this at World Time Attack Challenge in Sydney last year, and this is the Mighty Mouse Honda CRX, which is one of the crowd favorites. It definitely punches well above its weight, and we've got an in-depth interview that goes over how the car was designed, what components are included in the car, and also get a bit of insight into the thought process that goes into building a car at that particular level. The next video we've got as well is a video that we've just recently released. It's called the GM Rich After Reflash video. So this explains the rich after reflash phenomenon that a lot of you using the HP Tuner software on late model GM vehicles will have experienced. It's a real frustration where when you reflash the car after it's at operating temperature, the engine for a matter of about 15 minutes or more will go excessively rich. So just recently HP Tuners, along with one of their forum members, found the particular table that results in this phenomenon, and they've developed a fix. So this particular video goes into a little bit of detail in exactly what's causing this rich after reflash phenomenon and how you can get around it. And literally this will save hours for anyone who's tuning late model GM vehicles on the HP Tuners platform. So you can check that out. Now, on that note, if you do want to view these videos and stay up to date with the latest what we're doing with High Performance Academy in terms of the videos we're producing, please subscribe to our YouTube channel. You can find us by searching Learn to Tune on YouTube. We've got a huge amount of really great material in there, interviews with some of the most experienced and well-known tuners and car builders from all around the world. In terms of that video that we looked at with Mighty Mouse, as I said, that was shot at World Time Attack Challenge in Sydney Motorsport Park last year. Ben and I will be heading back to Sydney to World Time Attack Challenge this year in the middle of October. We're really looking forward to that. We've been there for I think the last 3 years, and it's always great to get over there and see what people have been doing to their cars in the off season. Certainly at the moment, that's one of the most exciting forms of motorsport. I think it's not that common to see a racing class where there really are so few rules, and it's really allowing car builders and tuners to push both the chassis as well as the engines to the absolute limit. And we're seeing some incredible lap times being run at World Time Attack Challenge, particularly given that all of the cars are forced to run on a dot legal tyre. So the current open class cars are lapping considerably faster than the likes of the V8 supercars, which obviously are running on a full slick and developed just about no expense spared. So really impressive what is being achieved there. Okay, we'll jump into some questions. So if you do have any questions, please ask them now in the comments, and Ben will transfer those through to me so we can hopefully answer them. Looks like at the moment we've only got one from Bevan Dunlop. Was the Plex Micro SDM able to record and play back? Yeah, it does have a data logging function, and one of the cool aspects with that is you can do that from the unit itself. Now, I'll be perfectly honest, at the moment the data logging aspect of the Plex is not one that I've personally played around with too much, so I can't comment too much more on that, but yeah, it does provide really basic data logging control. Just the one question. All right, I'm gonna have to expect a little bit more from you guys from our show next week, but I can't expect too much right now because this is our first show and no one really knew what to expect. But this is the perfect time to get answers to any tuning questions you've got, or of course any of the products that we've been talking about during this segment. Okay, that's the end of our first show. Thanks for joining us. I hope you've really enjoyed it. I hope you've learnt something new, and we look forward to bringing you our next show next week. Thanks, guys.